Hello everyone, welcome back to the course on measurement and instrumentation, and today is the second lecture of 11th week. We are discussing our 5th module on data acquisition system. In the previous class we discussed about a generic view of a data acquisition system, and we have seen different ways to classify data acquisition system, and we have also seen that there are two different ways in which data acquisition system can be classified. We have seen it as analog data acquisition system and digital data acquisition system. Today we are going to learn about the analog data acquisition system, and maybe in the next class we will discuss about the digital data acquisition system. Okay? So an analog data acquisition system is an instrument that measures or instrument system basically that measures real world physical variables, including the temperature, pressure, humidity, etc., that we have seen in the previous class also, using different sensors and transducers, and processes the resulting analog signal through analog circuits and its component like amplifier, filters, recorders and so on, while maintaining the signal in continuous time as well as continuous amplitude form. Okay. So you can say that it is a system that measures these variables and processes the signal entirely in analog form without actually bothering about processing the digital data. Okay. So in this system the signal remains mostly in the continuous form throughout the measurement, conditioning as well as in the transmission. Similarly, it also possesses the same form while it is recorded or say displayed. Okay. So analog data acquisition system typically consists of several parts. Like any DAS, it has a transducer, a signal conditioning unit, multiplexer and display, recorder and so on. We will see that there are some other parts or components of this also along with these components. Okay. So the first component is the transducer. We have seen that in detail in our previous modules, as well as we talked about them in our last class also, that the current and voltages which are obtained from the transducer is proportional to the quantity, or maybe it's say the proportionality can be linear or non-linear depending on what kind of transducer we are using, to the quantity that or the physical parameter that we are measuring, and this is used as an input to the data acquisition system. Particularly the output of the transducer is fed into a signal conditioning unit. Okay. The signal conditioning unit in an analog data acquisition system plays a very crucial role in preparing this raw sensor signal for accurate measurement and processing. It primarily performs three different roles, including the amplification of the signal, filtering of the noise and other signals, as well as it also perform isolation role. Okay. We have seen isolation in brief in our last class. Okay. Then the next stage is a multiplexer or mux. Multiplexer is the process of sharing a single channel among multiple input signal that we have seen previously also. Okay. Therefore, a multiplexer accepts multiple analog input and connect them sequentially to the output. Okay. Let's take one example. Okay, like this is a multiplexer. Let me call it a mux. Okay, I have multiple input lines. Say I have input 0, 1, 2 and 3. Okay, and I want one output at one time. Okay, so usually it is done by the select pins. So mux directs one of the input to its output line by using these select lines. Okay. And the typical multiplexer will contain these inputs, select lines and one output. Okay. Now the selection input determines the input that should be connected to the output. So these lines actually, these select pins actually choose which input has to be selected at one particular time and is displayed or is connected to the output. Okay. So you can consider it as an electronic switch that selects one among multiple to the output. Okay. So you can say that a mux is a digital switch that has multiple inputs or multiple sources and one single output or one single destination. These select lines determine which input is connected to the output. Okay. Now depending on how many inputs are there, of course output is fixed, that is fixed in number, means that is 1. Okay. You can have 2 to 1 mux lines. So, you have two inputs, say input 0, input 1. So, let me call this input 0, input 1, okay, and this mux depending on this select line will select one of the input and then display at the output one at a time. Okay. Similarly, you have 4 to 1 mux where you have two select lines. So, depending on 2 to the power n, which is number of inputs, this is number of inputs, okay, I will have n number of select lines. Okay. So, like I have 2 to 1 mux means that I have one select line only. One select line depending on it is 0 or 1, okay, it will select the input line. Similarly, for 4 to 1 mux I have two select lines. For 8 to 1 mux I have 3 select line, and 2 to the power 4, say 2 power 4 is this 16 to 1 mux I have 4 select lines. Okay. Like one of the example of this analog data acquisition system can be this. So, I have a mux, okay, I have 4 inputs and they are connected to say some home media hub, maybe a smart projector, okay, say this is a smart projector and it is displaying whatever is connected. Okay. Now, say I have two select lines B and A, okay. Now, when I have both B and A as 0 0, okay, at this particular instance, say D naught is input D naught is selected, means the display from this TV will be displayed over this projector. Okay. Now, you do not need multiple projectors to project something from TV, for laptop, from mobile or from game console. So, say in one go you are watching TV, that can be selected using this mux and that will be displayed. Okay. Now, when I have B and A as 0 and 1, then the content of the laptop will be displayed on the projector because this mux is selecting D1 input. Okay. Now, similarly, if I have B and A as 1 and 0, okay, the content from this mobile will be displayed, and similarly when I have 1 1 means that D3 line is selected, means the gaming console is getting projected over here. Okay. So, this mux play a very crucial role in a data acquisition system. Okay. Now, you can see this in better sense. I have 3 inputs D0, 1, 2 and 3 and 2 select lines B and A, and you can see their connections. Okay. I have this AND gates. Okay. So, this is AND gate number 0, 1, 2 and 3. Okay. If you have not studied digital electronics, I would request you that you have a look on these gates. Okay. What are these? These are all are digital gates, okay, logic gates. Okay. Their input and output are usually denoted by a truth table, okay, like say I have two input to this AND gate. For example, inputs are X and Y. Okay. Now, this Z, which is the output, okay, will be equal to X, Y. Okay. Similarly, I have OR gates. Okay. If I have input as X and Y, the output Z will be X plus Y, right. Similarly, you have NAND gate, NOR gate, XOR gate, XOR gate, XNOR gate and so on. Okay. I will request you that if you are not aware about these gates, please have a look on them. Okay. That will be helpful in understanding these concepts. Okay. But in very brief, you can see that this is AND gate, okay, and this is say a OR gate, since we are using them here, okay, and we are also using a NOT gate. So, let me, so if I have a X as an input, this output Y is inverse of X. Okay. So, let me write the truth table of these gates, okay, because usually these gates are understood better by their truth tables. Okay. Now, say I have two inputs, say for example, for AND gate, okay, I have two inputs x and y. They can have values like 0, 0, 0, 1, 1, 0 and 1, 1, right. When you have input both x and y as 0, or in more generic term, you can understand that when both inputs are low, output will be low. When one of the input goes up or goes high and x is say 0 out and y is 1, or x is low and y is high, still the output remains at low. Okay. Now, when you have x as 1 or high and y as 0, in that case also the output remains low. However, when both goes up or both are high, when x is also high, say 1, and y is also high, say again 1, in that case the output becomes 1. Means that for an AND gate, output to go high, both the inputs has to be high. All right. Similarly, for OR gate, okay, this was your OR gate. Okay. If I have inputs like x and y as 0, 0, 0, 1, 1, 0 and 1, 1, okay, the output when both are low, it is low. Okay. Now, when x is low and y is high, or x is 0, y is 1, in this case the output goes up and now I have output as 1. Okay. Similarly, when x becomes 1 or x becomes high and y becomes 0, in that case also output will become 1, and when both are high, in that case also z become 1. You can see that when both the inputs are low, in only in this condition the output is 0, but if any one of the input goes high or even both goes high, output becomes 1. Okay. Now, using these gates, this mux is constructed. Okay. This NOT gate, as I have mentioned, that the truth table is very simple. So, if x is the input and y is the output, if x is 0, NOT means at the output you will have just reverse of this or 1. So, if input goes 0, output goes high. Similarly, when input goes high, the output should be 0. Now, you can see this configuration, and this is the truth table of this particular configuration. Okay. Let us understand this with one of the example and then we will proceed. Now, say consider this first condition when both b and a are 0. When both b and a are 0 means that b is connected through this NOT gate to this point or to the input of this, say number 0 AND gate. All right. So, through this NOT gate it is connected over here. I have input as D0 and means that the input here is 1 because B is connected through this NOT gate over here. So, B was 0, that is why this is 1. Okay. Now, when I have A as 0, again through this NOT gate it is connected to the input here. So, I have input as 1. Okay. Now, we have seen that for AND gate, when both the input or say all the inputs goes high, the output will be high, or if any goes low, output will be low. Okay. Now, both are high. Okay. The output will be highly dependent on D naught. If D naught is going up or going high, means all the inputs are 1. In that case, output will be high. Now, when D naught goes to 0, means that one of the input is 0, means that output will be 0. Means that this D naught line is directly influencing the output from this number 0 AND gate, or I can say that the output is D naught. If you go mathematically, you can understand it more using the mathematical terminology like B A into D naught. So, output will be this, and accordingly you can select your line. Okay. We are understanding it through more generic way. So, output here is D naught. Okay. Now, this is going to the input of this OR gate, and we have seen that for OR, if any one of the input goes high, it will be high. Okay. Now, similarly, I can find output of this and output of this. Okay. Means that output of number 1D gate, number 1 AND gate, number 2 AND gate, number 3 AND gate, okay, and all are say input to this OR, okay, and output is summation of all, because we have seen that output of OR gate is x plus y, or say in this case D naught plus this input plus this input plus this input. Okay. Now, say D1 is having some value, maybe 0 or 1, okay, and it is fed to AND gate 1. This is AND gate 1, it is fed into it. Okay. Now, if you see B naught is connected over here, okay, so this is 1. Okay. Now, if you see A is directly connected over here. Now, A naught is not connected, A is connected over here, means that one of the input is going low, and we have seen that for AND gate, if all goes up, then only output will be up, otherwise it will be 0. Means that the output will not depend on D1. D1 can be anything, it can go low, it can go up, but the output of this NOT gate, this AND gate 1 will always remain 0, because one of the input has gone already 0 by this select lines. Okay. Now, when it is 0, means that it is getting fed into this as 0. Similarly, you can find that output of AND gate number 2 is also 0 and output of AND gate number 3 is also 0. Okay. Means that whatever you are feeding over here in the input of this OR gate is 0 plus 0 plus 0 plus D naught. Means that your output is D naught, and exactly it is shown over here. Similarly, you can choose your own configuration of B and A. Okay, you can choose 0 and 1, 1 and 0 and 1 and 1 and try to understand this configuration, and you will find that at one go only one input is selected. Like for 0 0, we have seen that line D naught is selected. Similarly, for 0 1, D1 is selected. For 1 0, you have D2 in the output, and for 1 and 1, you have D3 at the output. Okay. So, this is 4 to 1 mux. Okay. Similarly, this is more complicated mux where you have 8 lines to select, and then you have 2 to the power 3 means 3 select lines, right, and then output will be 1 of this D0 to D7 at one time. Okay. Now, there are two methods of multiplexing that this analog data acquisition system uses. One is time division multiplexing and another is the frequency division multiplexing. Okay. Let us understand them one by one. Okay. Let us understand first the time division multiplexing. Okay. In time division multiplexing, the information from different measuring point is transmitted serially on the same communication channel. Okay. The measurements are sampled sequentially and transmitted until all the quantities has been sampled. Okay. Once the entire set of quantities has been sampled, the process is repeated cyclically. The time to complete transmission of all measurements may be very small, so that one quantity cannot change during the interval between the sampling. Okay. The sequence in which different signals are transmitted over the shared channel is not random and is controlled in certain way. Okay. Now, this controlling is done by two methods. One is the cyclic control and another is the command based control. Cyclic controller mainly uses a pulse generator or a clock, while the command based control uses programmable logic circuits. Okay. Now, let us try to understand this cyclic control using a pulse generator. A pulse generator or a clock acts as a timing reference over here. Okay. It continuously produces pulse that switches the multiplexer from one channel to the next and assign fixed time slot to every signal. Okay. Now, this results in a repeating cycle, like once you have samples like S1, S2, S3 to Sn passed over certain communication channel, then it is again repeated and again it starts transmitting S1, S2, S3. Okay. Now, every signal is sampled and transmitted periodically in the same order. Okay. Now, the second way is the command based control or a programmable control, where instead of a fixed cycle, the order is controlled by control logic and microprocessor is used for providing the controlling command. Okay. Signals are transmitted here based on the priority. Okay. And event occurrence is determined by again the priority of the signal. Okay. Like, let me give one example, that say I have a communication channel. Okay. I am using a time division multiplexing. Okay. Now, what I am trying to do is I am using the same channel, okay, to transmit say temperature data of a plant, okay, humidity data and say pressure data of certain chamber, pressure of the chamber. So, I am using the same communication channel to transmit three different data, which is transmitted using time division multiplexing. Okay. Means that initially say for 10 seconds I am transmitting the temperature data, say for next 5 seconds I am passing out the humidity data, and for another say 8 seconds I am transmitting say pressure data. Now, when I say command based control, means that at say particular time, say at 9:35 or say at the end of 101 minute of measurement, minute of certain measurement, say if I require the humidity data and I am preferring it over a temperature or pressure of the chamber data. Okay. In that case, my previous way of transmitting data, which was based on a cyclic control, may not prioritize the humidity data. Okay. Or say at that particular time, say if it was sequenced to transmit say temperature data, it will only transmit the temperature data. But I want at this particular moment the humidity data. There this command based control or a programmable control based TDM can help me by prioritizing the humidity data. Okay. So, that is why I mentioned that the signals are transmitted based on priority, event occurrence and specific measurement requirements of the user. Okay. So, TDM is more effective when transmitting slow changing low bandwidth signals, for example, these physical sensors that I have just mentioned, including temperature, pressure or humidity data. Okay. So, usually if you see temperature typically changes very slowly. So, it does not need to be measured or transmitted very continuously. Okay, you can segregate the measurement, like instead of sending temperature data at interval of about say 10 second is usually sufficient for accurate monitoring. So you do not have to send it for every second. Okay, you can send it for 10 second or something. Okay, because we know that say if I am monitoring say ambient temperature, within this 10 second that temperature is not, of course requirement may vary, but in general this is usually avoided, and say temperature is sent for every 10 second or 15 second or so on. Okay, similarly for humidity also, there can be very little cases where humidity can change say from 25% RH to say it jump to say 90% RH. The jump can be like 25 to say 27 or 26% RH or so on within this 10 second. Okay, that's why I mentioned initially that they are usually preferred for low bandwidth signals. Okay. Now, if a dedicated RF communication link were used exclusively for transmitting these low bandwidth data, most of the channel's capacity would remain unused during the time between the consecutive measurements. Okay. So, this will lead to inefficient utilization of bandwidth as well as the other resources. Okay. So, to overcome this inefficiency, time division multiplexing is employed, and the communication channel is divided into multiple time slots, and during the dead time, which is basically the interval between successive, in the case of temperature transmission. Okay, this is the temperature transmission, say at time 0 I have transmitted a temperature signal, and again at time equal to say 10 second I have transmitted a temperature signal. Then in between this time 0 to 10 second I am calling this time as dead time. All right. So, the communication channel is divided into multiple time slots, and during the dead time, which is this particular interval that I have just mentioned, the same channel is used to transmit data from other sensors or other process variables, say for example other low bandwidth signals like pressure or some flow rate or say gas concentration in that particular bandwidth. So, you are using that dead time to transmit the other important data. Okay. Now, each signal is allocated a specific time slot, ensuring that all measurements are transmitted in a organized and non-overlapping manner. Okay. As a result, the TDM significantly improves the channel utilization and reduces the need of multiple communication links for temperature separately, for humidity separately, for pressure or flow separately. We do not require that, and this actually enhances the utilization of the channel. Okay. So, this TDM allow a single system to handle multiple sensor input more efficiently. Okay. This makes it highly suitable for industrial data acquisition and telemetry systems, where many low speed signals need to be monitored over a shared communication medium. Okay. At the receiving station, the system must be, however, be capable to reconstruct the signal that has been transmitted. Okay. So, demultiplexing becomes very crucial in this case. Okay. So, separating back from the original signal into individual signal correspond to the original measurand is very important in this case. Okay. Because multiple signals are transmitted over the same channel using time division multiplexing. Okay. If you have that kind of arrangement, the data arrives in sequential time shared format, and if you do not take care of demultiplexing, in that case the issue will be like say for 0 to 10 second for example. So, temperature was sent at time equal to 0 and temperature was sent at time equal to say 10 second. In between say at 7th second, okay, say pressure was sent, okay, the pressure data was sent, and say at 5th second, okay, say other signal, for example say flow rate was sent. Okay. Now, at the demultiplexing end or at the receiver end, if you are not able to, or if you miss any of this time sequence, okay, you may end up getting all the erroneous data. Okay. Like if you by mistake or by some other error, if you missed and say you are considering 8th signal which was not carrying any information as say temperature data, or pressure data, all other sequences will go wrong. Okay. So, therefore, the demultiplexing is also very crucial in case of TDM, and therefore, it is essential for the receiver to accurately track timing or identify each time slot, so that it can correctly associate each portion of the received data with its respective source. Okay. Now, designing a time division multiplexing system may sometime be very complex, but let us try to understand a electronic time division multiplexing system with one simple example. Okay. This is one of the typical example for electronic time division multiplexing. Okay. You can see that there are number of switches and there is a logic and controls circuit over here. You are now acquainted with this gate. This is a D gate. Okay. This particular is inverter. Okay. This is a time delay circuit. This is again a inverter, and this is a bridge of diodes. Okay. Now, let me call this diode as D1. This is say D2. This is D3, and this is say D4. Okay. I have 4 different diodes, D1, D2, D3 and D4. Okay. And say this is the first input placed, and this is the output, and this is fed back. Okay. I also have a clock pulse generator over here. Okay. So, there are 8 input circuits which are successively connected to the output circuit through this diode bridge. Okay. These are, you can say, different sensors or signal channels. Okay. Now, this area that you are seeing in this dashed line is a logic and control circuit which decides which input is connected to the output. Okay. Its major job is to synchronize switching with the clock, ensuring only one channel is active at a time and generate proper timing intervals. Okay. Now, when junction A, this junction A is positive with respect to junction B, now what will happen that this diode D1 and diode D2, say I am calling this A to be positive, means that this diode D1 and D2 will be in the reverse bias condition. Okay. Now, I am telling that this B is also say at, this was at positive terminal. So, this is say at relatively negative voltage, and means that these 2 diodes, say D3 and D4, are now connected through to a negative terminal, means that this D3 and D4 are also in the reverse bias condition. Okay. Now, when you have this reverse bias condition, okay, means that the diodes in the bridge will have infinite resistances. Okay. And the circuit between this C and D will be kind of open circuit effectively. Okay. Now, consider the opposite case when the junction B is positive with respect to point A. Okay. In that case, if you see diode D1, D2, they are connected to a negative terminal, means that they are forward biased. The biasing in this case is forward, and this is in positive terminal, means that D3 and D4 are also forward biased. Alright. So, when junction B is positive with respect to point A, the diodes are forward biased, means they will have very low resistance, and the bridge becomes a kind of balanced bridge circuit with very low resistance arms. Okay. And the potential of junction C and D will be same. Then the voltage at C is equal to the input voltage at D, or the circuit from C to D is a closed circuit. Okay. Earlier, when they were reverse bias, you can say that it was kind of open circuit. Okay. Now, the switching circuit that controls the potential at point A and B is operated by the application of this clock pulse, which is generated by this clock pulse generator, and reset signal at the first and second input respectively of the first and circuit of the control system. I am calling this first and this I am calling as second AND. Okay. Now, this clock pulse, if you see, they are fed into each electronic switch to this here everywhere, and this is the reset signal which is fed into this particular first AND. Okay. The clock pulse is of very short duration and has a magnitude of say plus 15 volt. Please note that when I say plus 15 volt, I mean to say that the pulse is high. When it is minus 15 volt, I mean to say it is at low. So, you can understand it from digital point of view that this is 1 and this is 0. So, plus 15 volt I am calling 1 and minus 15 volt I am calling 0. Okay. So, the clock pulse is of very short duration and say has a magnitude of plus 15 volt, and during the remainder of the time it is at minus 15 volt. Okay. The reset signal is generated by the operation of the preceding switching circuit. We will see how. Okay. And this reset signal is applied to the next switching circuit before the clock pulse is actually generated. Okay. It is 15 volt plus 15 volt during this part of the cycle and remains at minus 15 volt during the rest of the cycle. Okay. Now, these two pulses produces a short plus 15 volt pulse at the output of the first AND circuit by say the clock pulse is say 15. Okay. And this input is also 15. Okay. So, both are high means that output will be high. Both are 1 means output of this AND gate will be 1, or you can say plus 15 volt. Okay. When both reset and this clock were 15 means that output will also be 15. Okay. Now, this 15 is fed into the first input of this second AND gate. This is the second AND gate. Okay. In this system. Okay. The second input to the second AND was already 15. Okay. Now, these two pulses produce another 15 at say this output E. Okay. Which is fed back to the input of the second AND gate through this delay and this inverter like this. So, this is at output and this is fed back to the input. Okay. Now, this locks the second AND circuit in the first one position and keep the output of the second AND circuit at junction E as plus 15 as long as the second input to the second AND circuit is 15 volt. Till it goes to minus 15 volt, the output will remain plus 15, and that is why I told that it locks it into a higher position or at high or say at 1. Okay. Now, the second input to the second AND circuit is feedback circuit from the junction E. Okay. This is the junction E. Okay. Through a time delay circuit and a NOT circuit. This is the NOT circuit I am talking about, and this is the, if this D and this D is confusing, let me call this capital D or a delay circuit. Okay. The output of the time delay circuit is also applied to the reset of the next switch to be operated. Now, this is also fed to the next input. So, initially say input 1 was applied and now it is applied to input 2, which is the second input in the sequence. Okay. So, the output of the time delay circuit is also applied to this. Okay. Please note that when it is fed to this input, there is a inverter, but here there is no inverter. Okay. So, you can say that the output of the time delay circuit is also applied to the reset of the next switch to be operated. Okay. The plus 15 volt pulse from junction E will arrive at the reset of the next switch to be operated just before the next clock pulse, and the switch will operate at the arrival of the next clock pulse. At the same time, the voltage through the NOT circuit will shut off the switch that has been in the operation. Here it was switch 1. Okay. And the potential of point E will become negative or it will go low. minus 15 volt. And this will keep at minus 15 volt until the two inputs to the first AND circuit of the switch are both going high, or both are again plus 15 volt. Then only it can go back from minus 15 to plus 15, because we have already seen the characteristic of a AND gate. Okay. Now, when junction E is plus 15 volt, junction A will be minus 15 volt, because it is converted to, I am not considering any voltage drop across it. So, it will be around minus 15 volt, okay, and this B will be at plus 15 volt, alright. B will be 15 volt when A will be at minus 15 volt, okay. Now, junction A, which is supplied from the junction E through an inverter, is now minus 15 volt and B is at plus 15 volt, okay. Now, this makes the voltage at D at this point equal to the voltage at C, and please note that voltage at C is nothing but the input, okay. Input voltage 1 is applied to the output of this switch. When the junction E is at minus 15 volt, the reverse will happen and hence there will be a reset in the circuit, okay. These switches uses here are all electronic switches and are activated only by the digital logic levels that are placed over here. I have initially mentioned that this is the digital logic and control circuit, and you have seen that in this particular time input 1 is selected. Similarly, it keep on changing the input from 1 to 8, say, for certain time sequentially over here, okay. So, first 1, then 2, 3 and so on, okay. Now, this is a typical example of electronic time division multiplexing, okay. There are several advantages of using this time division multiplexing, okay, like it ensure efficient utilization of single transmission channel for multiple signals, particularly when you have the low bandwidth signals like temperature, pressure, humidity and so on, okay. Since you are not using any frequency division multiplexing, no frequency overlapping or inter-channel interference happens, okay. They have a very simple implementation even in the digital system, and flexible channel allocation is possible by changing time slot for different signals depending on, again, on priority. So, say if you want temperature to be monitored for more time, humidity for less time, you can do all those permutation and combination in this circuit, okay. They have very good noise immunity compared to the analog multiplexing, and TDM is very popular for digital multiplexing only, okay. They have different limitations as well, like they require precise synchronization between transmitter and receiver. In fact, the TDM are also of two class, one is the synchronous TDM and another is asynchronous TDM. We have not discussed that, but you can say that they require precise synchronization between transmitter and receiver, okay. Time slot wastage is there because some channels may have no data to transmit, okay, at particular time event, okay. System complexity increases with large number of channels, okay. There is a latency or transmission delay due to sequential time sharing between in the channel between different signals, okay. And they need high speed switching and processing hardware because you are selecting one after another in a very short time. So, to ensure that you are efficiently using particular channel efficiently, these devices or the hardwares should be very fast, okay. Therefore, to overcome these limitations of TDM, we have frequency division multiplexing or FDM, okay. This is needed when simultaneous transmission of continuous analog signals is required and there is, I mean, kind of real time monitoring of all the signals are required, okay. So, when there is no tolerance, I would say, for time delay, FDM become very important, okay. They are suitable for systems with synchronization required in TDM is difficult to maintain. So, for those cases FDM are important and they allow independent transmission of multiple signals on different frequency bands, and that is why I mentioned that real time transmission without any delay is possible with the FDM. So, in our next class we will continue our discussion on FDM, and we will also see some other parts or components of an analog DAS, okay, and then we will see the digital DAS system also. Okay. So, please connect in the next lecture also. Thank you.